My name is Brian Field, and I'm going to talk about how we're using moloch in the networking space. Okay, so a couple of things. I'm an outlier here in the sense of I don't do anything in security. I'm a network guy, right? So I'm going to be out there. I've only been using moloch since May, so I'm a beginner, right? And I flew in this morning from Denver, so I've been up since 1 o'clock Pacific time, which means I'm jamming on the coffee. And if you guys don't ask questions, I'm going to be done in about 8 minutes, all right? So I really want this to be a discussion, okay? And again, I think this domain is going to be totally different than what most people are thinking about, so hopefully it'll get some discussion going here. Okay, but the title of the talk is More Data is Good, but Good Data is Better. And again, it's around networking. It's around some problems we have in the networking space. Just to give you a little bit of background, 20 years in the cable service provider space, PhD in computer science, a bunch of patents, did a whole bunch of architecture work converging voice, video, and data onto a common IP infrastructure, laying multicast on top of that. At the time we were doing the multicast, it was thousands of multicast groups, hundreds of gigabits of data, no operational tools. So we spent a bunch of time building operational tools for looking at multicast data end to end, which resulted in a bunch of patents, and then also involved in laying commercial services on top of this IP infrastructure. So that's kind of my background. Since then, I did a bunch of work in the beginning of CDN. If you ever heard of Xfinity, I was part of that when it was kind of in a startup mode. Did a bunch of work with network virtualization, the idea here being leveraging virtualization to allow us to quickly prototype network architectures and to do analytics on those and whatnot. Involved in streaming telemetry from the perspective of, if we're testing out a new architecture of some sort, when we want to stream telemetry out of that, move to this new paradigm, we did a bunch of work in that space. And then that got me to analytics. And again, what I'm going to talk about today is applying or doing network analytics on network data, but we're going to be using moloch as a key part of that. And again, the focus now is applying the above domain knowledge, again, a network architect for a long time, into the analytics space, okay? Okay, so here's the problem that we've run into. And we've seen this in a bunch of different service provider networks, and that is the following. We have undetected network issues. So what that means is, imagine all the data you're getting out of the network, right? A bunch of routers and whatnot, and there's some sort of event that happens where services are impacted, but the data you're getting out of the network is inadequate. It's inadequate in the sense that it's not telling you a problem exists. The way we find these problems is customers call us, or customers send us trace routes, or services that were operating in the network become aware of a problem. So the existing network operational data is inadequate to find these sorts of issues, okay? Now, what are the examples of these types of problems? One example is a forwarding loop. So imagine something's happening in the network, some announcements come in some particular way, and a forwarding loop gets formed. For the most part, you can't detect that via existing network operational data. Okay, so the way we find out is customers call or services call and basically send us a trace route and showing the forwarding loop. Another example, and this happens in any service provider network, where you're changing ACLs to bring them up the template or whatever, you don't realize some service is leveraging some prefix that just got removed by the ACL. So people are making ACL changes to bring routers up to a particular configuration, and services go offline. And they can't figure that out based on the existing network operational data. The way they become aware of it is the service folks contacts the ops folks basically go back and try to figure out what changes were made in the network. Oh, an ACL change was made on 42 different routers, it's likely that, okay? Similar sorts of thing, unexpected null routes, right? So imagine you're making changes on your peering router, you unexpectedly expose, some null route that's being used to kind of propagate BGP routing announcements, and you get traffic that gets dropped silently. Again, customers are offline, and there's nothing present on the router that explicitly says you just broke something, okay? Another one where if you have rogue routing announcements, V6 routing announcements in data centers, that's been shown to take V6 off-net traffic offline. Again, it's totally it's almost like a fever. It's a low-grade fever where it's not explicitly breaking services because chances are your data center is V4 and V6. Applications that can't go off-net V6 will work over V4, but the network is operating in a degraded mode. And the things regarding inconsistent MTUs. So there's these sets of problems where the existing network operational data doesn't give us the insight to find them. It's customers, it's services that are telling us there's a problem that takes tens of minutes, hours maybe, of the service being down or impacted because we don't have the right data. So what is this existing network operational data? It tends to be things like show commands, syslog, SNMP, streaming telemetry, and Openconfig. And the paradigm I'm trying to share here is it's the same data we've been getting for 20 years. Okay, so maybe I'm dating myself here, but a long time ago I bought this album, on vinyl, right? And then, a couple years later, my brother got a car, so I bought, the 8-track for it so I could listen to it in the car, right? And then I got my Walkman, right? So I bought it in cassette, right? And then, CDs came out, so I got the digital version, right? And then I got the MP3 version, right? So basically what I'm suggesting or what I'm saying here is the data we're getting out of the network today, it's the same freaking data. It's just kind of a different way we're packaging the data, okay? And the other problem with the data is that it tends to be low fidelity. It's like a counter which changes over time, okay? Or maybe a binary sort of condition. So, the data that we're getting out is like the same data we've been getting for 20 years, and it tends to be low fidelity data. Low fidelity means it's generating haystacks, and then we're searching for needles in those haystacks. Now, streaming is this new paradigm that, is working in the routing space. And the benefit or the beauty of streaming is that it allows you to generate or to send more data. It's more efficient to stream content or stream network operational data out of the routers than to do SNMP queries or show commands. That sounds great. But what it means is you're generating more haystacks, right, that need to be searched. Okay, so the latest kind of technology that's being used to kind of help find these sorts of problems is to say, okay, we're getting all this data. Maybe what we need to do is apply machine learning or AI to the data. And so there's a lot of energy going into it and some hype, basically, as if this is going to be some magic pixie dust that's going to find all these sorts of issues. But if you think about ML, if you think about it, like the underlying theory to ML is no matter how powerful your algorithm or no matter how much compute you have, if you don't have the right data, it's not going to get you where you need to be. You got to have the right data for ML and AI to kind of provide value for you. Okay, so it's not a magic pixie dust that's going to find all of these different sorts of problems. Okay, so thinking about this, we have existing network operational data. It's low fidelity. Throwing ML and AI may not be the right answer to it. Is there other data available on the router that might give us the insights that we need? So is there some other high fidelity network operational data feed that we're overlooking? Well, to think about it, maybe what we need to do is think about how a router works. So at a high level, I've got a picture of a router here. At the bottom, I've got a bunch of interfaces. I've got a CPU. And basically what I do is I feed into that CPU some configs, and then I basically, set up routing protocols to give it information about, so it can build a forwarding state. And it basically takes that forwarding information, the fib information, and pushes it down to the line cards, okay? And then, I've got traffic that gets hardware searched through the interfaces. I can generate NetFlow data, and then I've got all the existing network operational data that I get out of the boxes today. Again, that's lots and lots of haystacks. Is there anything else on this router that might be a high fidelity feed of information that we're totally overlooking? The answer is yes. Inside of a router, between those interfaces and the CPU, is an Ethernet interface. It's a logical Ethernet interface over which very useful information flows. All the routing protocols flow and all the kind of negative traffic flows. So it turns out, we've been kind of in this paradigm of using, SNMP data and show command output data and syslog data to try to figure out what's going on, and we're totally overlooking high fidelity feed of information on the routers today. It's the traffic on this control plane. Okay, so just kind of going through what this traffic is. It's routing traffic. So all the classic routing protocols that you would turn on for router, BGP, ISIS, OSPF, LLDP, blah, 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 blah. All the different protocols Andy was talking about are important protocols that we want to kind of have information about. That's all going over this control plane interface. There's a whole nother type of traffic that goes over this control plane interface called punt traffic, okay? So when you think about a router, you're basically building the fib and pushing it down to line cards and down to the interfaces with the hope that the traffic comes in on an interface, it matches on a TCAM entry that says, go out this particular interface. But if those rules, those hardware forwarding rules, if there's not a match for a packet, what happens is that packet gets punted to the CPU. And those punt packets are basically packets which are special case kinds of packets. There's something odd about them that requires special software handling, and that's why they're punted to the CPU. Examples of traffic like that would include a packet that comes in with a TTL equal 1, right? That's basically where the packet's counter, the header counter, is decreased down to 1, such that it hit an interface, the interface said, hey, I can't forward this because the TTL will be 0, so it punts it to the CPU. And then the CPU does something magic for us. It generates an ICMP TTL expired packet. It sends it back to the original device. So there's all this negative traffic, which is basically telling us special things are going on. We're not forwarding the traffic. It's special traffic that is somehow not able to be forwarded because it's special cases. And it turns out those special cases are a lot of the types of problems we're looking for. And then the other types of traffic we're seeing here includes management traffic. So someone SSHs into the box, or a gRPC thing kicks off to basically make configuration changes, and then all the existing network operational data. All of this data is on this logical control plane inside of a router. Okay. So there's nothing really special about the data. It's just Ethernet data, just like the data that you would see kind of like on a server. The nuance here is that there may be an additional header, an Ethernet header on it, so that the CPU can figure out what interface the traffic arrived on, right? Instead of a server having a single interface, a router is going to have potentially hundreds of interfaces, and traffic is going to be coming in over hundreds of interfaces. So the CPU needs to be able to demux and figure out, oh, this packet came in over gigi 42, right? So there may be some additional information in this, but it's basically vanilla Ethernet traffic. Okay, so I wanted to do this slide a little bit differently, but when you think about the data, the control plane data that's coming in, we're going to see the arrival of packets within a stream. So think about a BGP session, right? It's a TCP session, and we're getting BGP updates, prefixes being added or being announced, being withdrawn. We get the sequence of packets within a stream. But a router likely has multiple BGP sessions. So we've got multiple independent streams, right? If we capture the control plane traffic, we can not only see the arrival pattern of packets within an individual stream, but we can kind of see how the packets are intermixed across streams. And that's particularly important when we need to think about the IGP, the interior gateway protocol, which is basically building the topology. So the interaction between what might be happening at the IGP level, what might be happening at the BGP level, is going to drive the forwarding on the box itself. So being able to kind of see those layers of interaction are key. We're going to see the source of the packet, the destination of the packet, and then huge is going to be the payload of the packet. So when you think about all this data, it's like 5 different dimensions of useful data compared to what we typically get today out of show commands or models, which is evaluate, which is changing over time. So the idea here, the metaphor here is, the control plane data is like the sequence of clouds that are changing and moving over time, and what we have, the existing network operational data, is the shadows those clouds are casting. So today we're working from the shadows and trying to work back to clouds. If, on the other hand, we capture the control plane traffic, we're effectively capturing what's making those clouds right now. Does that make sense? Okay. So, when I first started working on this, I did a bunch of Googling. It's like, okay, great, I've got this use case, right? I want to get packet captures. I want to stream packet captures off my routing ecosystem. Wouldn't it be great if there was an open source, scalable, streaming packet capture, parsing, decorating, and storage platform? It took me a little while, it took me a couple days, but there is, and that's why we're all here, right? So the idea here is that we have this problem in the networking space. We've identified a really high fidelity feed of information that's based off of packets on the control plane, and we want to jam them into moloch. So here's kind of the high level architecture that we're thinking. So in the top, we've got, our routers up there. And again, this isn't limited to just routers. It's basically limited to any sort of device that has a control plane, right? So that include load balancers, it can include firewalls and whatnot. But we have a bunch of devices up there. And then what we want to do is we want to stream the control plane from those devices into MolochON. I want to make it clear here, we don't need physical taps to get this data. It's not like I need to basically have a physical tap on every interface on every router. I can basically SSH into the router and stream the captures over SSH back to a MolochON instance, and then basically feed it into the capture thing. So I'm going to have my network architecture, my network devices, streaming captures into MolochON. And as we know, MolochON is going to do the parsing, the decorating, and jam it into Elastic. It's also going to basically make, database of PCAPs. And then we're going to have, in our thinking here, we'll have Elastic. And then right now we're looking at Kibana as the UI. And then we're going to basically build analytics that are going to be based off of data in Elastic. That's going to give us the breadcrumbs to do more deeper dive analysis. But this is the high-level architecture we're looking at right now. And so Andy and I have talked about a bunch of different things in terms of feature requirements for MolochON. And one of the things I realized, it's probably valuable for me to think about what my analytic use case is. So my goal here is not just to make MolochON network protocol aware. My goal is to basically be able to build analytics, and even more importantly, open source analytics for networking sorts of problems. So I started looking at, well, how would I expect my analytics to work? How would that process happen? So the top line, or the text above the line, is kind of how things happen today. So something happens on the left-hand side. We don't know what happens. All of a sudden, say, a forwarding loop forms. Something happened, and all of a sudden, a forwarding loop formed. We're totally oblivious to the fact that a forwarding loop has formed. And basically, some amount of time later, tens of minutes, maybe hours, depending on the size of customers impacted, we get calls from customers. We send us trace routes. Ops gets engaged, and then we find a resolution. So that's kind of the paradigm today. Not an ideal paradigm. What we want to do is, if we, get the data into MolochON and then get the right breadcrumbs put into Elastic, what we should be able to do is devise signatures. So if I want to detect a forwarding loop, what I'm going to expect to see in the network is when the forwarding loop forms, packets are going to get caught in that loop. TTL will decrement down. All of a sudden, I'll get a slew of packets on the routers in the forwarding loop that are going to see packets with a TTL equal 1, which means they're going to be generating ICMP, TTL, unreachable packets. Guess what? That's my signature. As soon as the forwarding loop happens, I will see that happen, and that becomes my signature. The key here then is that after your signature, after you identify a particular problem, then the analytics are going to kick in. And so in this case, in terms of looking for a forwarding loop, if I see an increase in TTL equal 1 packets, my analytics are going to start to work backwards through the data. Okay, I just saw a whole bunch of TTL equal 1s on a set of routers. What changed? So the analytics are going to get kicked off to say, hey, it looks like a forwarding loop has formed. And what it will do is it will start to work backwards through the PCAP data, looking for particular things. In the case of a forwarding loop, you might look for BGP changes, or you might look for topology changes. But you start working backwards through the PCAP data to find what changed. And then you might go a step further. You might try to figure out who made that change. Was there a configuration change that triggered this BGP update which caused this forwarding loop? So you might continue to go back through the PCAP data. After you've identified, oh, this BGP update came in and caused a forwarding loop, can I go back in the data and identify by looking for SSH connections to the router or gRPC connections to the routers to see what change may have caused this forwarding loop to happen? So, from our perspective, we're looking at the analytics here to kind of figure out what kind of capabilities we need from MolochON and what decoration is doing with the data into Elastic. Okay. So this is kind of, our needs, and Andy touched on some of these. We have needs to support for Ethernet protocols. So ISIS is a pretty classic IGP that's used in the big scale service provider space, and it's not based on IP, it's based on Ethernet. LLDP is another protocol that's based on Ethernet, and we believe being able to see what's in LLDP is going to give us additional insights as well. It needs to be real time. And by this, what I mean is that we need to have this trade-off between how big the sessions are that are put into Elastic and how quickly we want to detect issues, right? So there's going to be this, we want to make it fast, but we realize we need to scale Elastic. We need to be able to correlate across streams, right? So I've got BGP updates coming in, and the forwarding that's being done with BGP is really going to be driven what my topology is, right? So I need to have the ability to kind of build analytics that can look across BGP streams, BGP sessions, different TCP sessions, and what might be happening at the IGP layer. And then across multiple devices, I've got networks of tens or hundreds of routers, so I need to have the ability to basically be looking at what's going on across all of those. And then I need to have the ability to efficiently walk backwards through the packet data. And kind of key here is this concept that we're calling lingua analytics. Lingua analytics. The idea here is that wouldn't it be great if there was a generic open source kind of way to express this analytic logic? Okay? And so the thing is that really where we want to get to is, wouldn't it be great if anyone could basically build an analytic and open source it, which said, hey, if you want to find a problem forwarding loop, here's how you would do it. Maybe it's a piece of code, but the logic or the code is basically built on a common representation for how you basically parse through a packet, what the fields in a packet are called. This is different than what Moloch is doing. This is a little bit further downstream. And so the net here is that the refinements that we think we need for Moloch to leverage or to go down this platform is Ethernet support, and then kind of a refined session sort of model, the ability to kind of make that session potentially smaller so that we can do things a little bit faster. Okay, so this is kind of like the overall ecosystem, and I've numbered it here, but again, the idea is that at the top, I've got my routers and applications that I'm basically all their control plane traffic. I am streaming it in some fashion, whether it's over SSH or maybe GRE, into a Moloch capture system. That's basically parsing the packets and then writing decorated information into Elastic. I can use Kibana as my UI, but I'm leveraging alerting that's happening on the Elastic data to kind of look for signatures. TTL equals TTL1 packets. If I see a spike in ICMP TTL equal 1, I likely have a forwarding loop. If I see administratively denied ICMP messages, I basically probably just hit a change in my ACL. So that negative traffic, we're going to start looking for those signatures, increases in those values as signatures. And then once we see something that says, hey, it looks like a forwarding loop, we basically kick off an analytic tool, which basically says, hey, looks like we've got a forwarding loop. It started at this time. The analytic tool will start taking over. And what it's going to do, it's going to say, okay, it looks like, looking at the TTL equal 1 packets, these are ICMP packets, inside of the payload of a ICMP unreachable, TTL expired, is actually the payload of the packet which was being dropped. So actually you can figure out what customers, what endpoints are being impacted by looking at what's inside of that ICMP payload. So then, that gives me the little breadcrumb I need to then go back and look for, was there a BGP change related to that prefix, or was there a topology change related to that prefix that would have impacted this behavior? And then again, you kind of work backwards through it. The thinking here is that, the analytics are going to be grabbing data out of Moloch Viewer, the PCAP data itself, and then basically using something like Src to basically convert the packets into this lingua analytic, this generic way of how you express the structure of a packet. So you can basically build generic open source tools for identification and troubleshooting of these types of events. Again, then you work backwards looking for the actual change itself. Okay, so I spent a lot of time talking about the negative sort of traffic that's on the router control plane, right? This is the stuff, I've made some change in a forwarding loop has happened and it went undetected, or I changed an ACL and I didn't realize it impacted customers until an hour or two later. There's another set of interesting things that we can do here. Remember, we're capturing the control plane, and I've just been focusing on kind of the negative stuff. All of that router control plane stuff is there. BGP is there, ISIS is there, and what we've been doing in the networking space is, trying to find ways of exporting that data. So, we've always wanted to get the data, the IGP, out of a network. And so, collectively with the routing providers, we built a protocol called BGP-LS. Anyone here heard of BGP-LS? Okay. BGP-LS, BGP link state, is basically a way of taking your IGP and putting it into BGP so that you can export it, okay? And so it's kind of this classic sort of routing sort of way for getting data out of the box, right? But what it means is that every time I make an IGP change in terms of if some new feature gets added to the IGP, I've got to update my IGP, then I've got to update the RFC for BGP-LS, then I got to go to the router vendors and basically say, please support this new feature, and 12, 18, 24 months later, I might get it, right? If, on the other hand, I capture the control plane traffic, I'm capturing the IGP natively. I no longer need another protocol to export that useful information for me. And then there's another protocol called BGP monitoring protocol, the same sort of thing. How can I see what BGP updates were actually sent to the box? So we created a completely new protocol, BGP or BMP, for doing that. Guess what? If I capture the control plane traffic directly, I have all that data. I don't need a router vendor to build a protocol to export that for me. So we think there's a lot of additional value by capturing the control plane traffic, and that it basically eliminates or reduces the features that we need from the routers themselves. And that lowers the bar, which is a good thing. Okay, so to wrap things up, what we've identified, what we think is going to be really, really valuable is that if we can capture the router control plane data, we think it's super high fidelity compared to the existing data. We think there's a lot of value in terms of capturing that data. We're going to leverage moloch as the capturing platform and parsing and decorating and putting it into Elastic. We build triggers off of the data that's going into Elastic, and then we start building analytics that work back way through the data, pulling PCAPs from moloch. And that, we're suggesting, we're proposing that the lingua analytics for the actual analytics themselves, how you would actually express the different fields in a packet that you need to have access to, maybe that's basically done via Wireshark. And I want to make it clear, because I know Andy brought this up, we're not suggesting that Wireshark decode be part of moloch. Moloch continues to do what it's doing. It does the decoration of stuff. And that downstream tools are going to be looking at the Elastic data, the decoration that's coming from moloch, and then doing further enhancements on the data, further processing of the data. And that's where Wireshark may be applicable. And the reason we want to do Wireshark there is because that seems like the common convention for how you would represent the different fields in a packet. So that enables us to open source network analytics. We want to group sources. Any service provider, any campus person, any PhD student should basically be able to build a network analytic in this sort of model. All right, that's it. Thank you.
You knew you weren't going to get out of that without any questions.
Oh, I want the questions. I want the questions.
This is entirely new to me, the concept that that router internal bus is actually available to us for tapping, and I'm going to try not to get the feedback. No, it's not you, it's me. Can you elaborate more on how exactly you go about doing that? Because I think that would be of great interest to some of our router teams.
Yeah, absolutely. So, working with Andy, we documented a new architecture that's up on the webpage, right? So the general idea is you just SSH into the router, where you basically, the device I use and I continue to use is the Arista box. So I'm just going to use that as an example. But you can basically SSH into the Arista, and then as part of the SSH, you run a command called TCP dump, where you basically stream the output to standard out. And then you basically write that into a pipe, and then you have moloch capture, read from the pipe. So that's one way for doing that.
Okay, great on an Arista where the underlying router operating system is Linux. Can you do that on iOS? Can you do it on Juniper?
You can do it on Juniper. And I'm not sure about vendor C, right? I think there are some capabilities in that space. So, but again, this is one of those things where if there's value here, then we have to just work with the vendor ecosystem to expose that. Was there another question?
Anybody? So thanks, Brian. He's doing a lot of work to kind of push us and adding new features and things into Moloch. So that's good for us. I think we're a little slow for him, but hopefully we can all work it out. But it's been great.